So today we jump to graphing trig functions, but we'll start with just graphing a linear function that we've been doing since freshman year and maybe even before. So typically when we didn't know how to graph like in slope-intercept form, we would take and plot points, pick an x, and then find out what the y would be. And we knew that from the equation, in this case, y would equal 3x plus 5. So you plug 1 in, get an answer, 2 in, get an answer for y, 3 in, get an answer for y, 4 in, get an answer for y, and we end up with something that looked like, I don't know, something that looked like this, right? After we plot all the different points. Okay? We're going to do the same thing for sine, cosine, and tangent. But to do that, we have to look at where those values come from. Now, once again, all these values come from our unit circle for sine, cosine, and tangent. And what we're going to do is we're going to graph f of x, or y, equals the sine of theta. And sine of theta equals the y value on the unit circle. So what I've done is I've laid out a little chart here, and we're going to actually find the easiest possible values on that unit circle. So we're going to look at pi over 2, pi, 3 pi over 2, and 2 pi. Now at 0, my y value is 0. At pi over 2, my y value is 1. At pi, my y value is 0 again. And at 3 pi over 2, my y value is negative 1. And if I graph all those, here's 0, 0, pi over 2 and 1, pi 0, 3 pi over 2, negative 1, and back at 2 pi we're at 0. And it repeats itself over and over again. They call this a periodic function because it repeats over and over. Now, if you look at this graph, a snapshot from where it starts to where it ends and then starts repeating is called a cycle of the graph. How long it takes to make that cycle happen is called the period. So you'll see here the period is 2 pi because the graph does its thing in 2 pi and then starts repeating. Okay, now the intervals, this is where I graphed it on, are pi over 2 because that's where we graphed it by pi over 2's because those are the easiest ways to get this done. To do cosine and tangent, we basically do the same thing, except for the cosine, we're looking for x values on the unit circle. So the x value at 0 is 1, at pi over 2 is 0, x value at pi is negative 1, x value at 3 pi over 2 is 0, and the x value at 2 pi, we're back at 1. Graph all those, here's the 1, pi over 2, 0, pi is negative 1, 3 pi over 2, and again, 2 pi is 1 again. This graph will repeat itself after 2 pi, so we call that period 2 pi. This is one cycle of the graph, and we graph these in pi over 2 intervals. We could use pi over 4 intervals, but they're approximations because we don't know. If I use pi over 4 right here, the exact value of root 2 over 2, we can do 1s and 0s pretty easy, so that's why we do it. So now if we look at tangent, tangent's a little different, okay? And you'll notice I've added a couple more points to my chart because here's what happens. When I use my unit circle and graph tangent, we know tangent is y over x value, right? And the tangent, or the y over x at 0 degrees, all right, that's the point 1, 0, so that's equal to 0. Now if I go to pi over 2, I get 0, 1, and I do a y over x value here, and I get an undefined value, so I've put an asymptote here. Go over to pi, and I get, once again, negative 1 and 0, or y over x is 0. Go to 3 pi over 2, I get 0, negative 1, and I put y over x, and that's undefined again, so another asymptote. And then, again, at 2 pi, I'm back to my value of 0. So, initially plugging in, I get nothing but singular points and then asymptotes. So what I really need is I need some intermediate points to get this done. So what I do is I use pi over 4 to find out the tangent value there. At pi over 4, I know the y and x value are both root 2 over 2, because I know my unit circle pretty well. Root 2 over 2 over root 2 over 2 is 1. So here's pi over 4, and it has a value of 1. And then I get to an asymptote. So this thing just keeps rising and rising and rising. And you can see that because if I do a unit circle and I get really close to pi over 2, my x value is really small, like 0.000 something, and my y value is relatively bigger, or 0.9999, etc. And 0.99999 over 0.000 is a really big number, so it goes up. But it's not going to hit that line because it gets undefined there. When I go to now at 3 pi over 4, I end up with a negative root 2 over 2 and a positive root 2 over 2. And I put those over each other and I get a negative 1, which is notated here. At 5 pi over 4, again, I get another value of positive 1 because I'm in the third quadrant. And at 7 pi over 4, I get another value of 1, except this time it's negative because I'm in the fourth quadrant. Okay, and you'll notice the tangent looks like this. It always increases. Number 1, it's always going up. All right, but you'll notice here that because of these asymptotes, we have to look at, well, what is a cycle of this? Well, a cycle is basically a snapshot of what it looks like before it takes and repeats itself. So I could look at a couple of different cycles. For instance, I could say from 0 to pi is a cycle. Or I could say from pi over 2 to 3 pi over 2 is a cycle, because it's going to go like this, and then it's going to do that again if I just continued the picture. All right? But my period in this case, how long does this take to repeat, or how long does one cycle cover? That's pi. And again, I'm using intervals of pi over 2. So like a lot of the other graphs that we have done, we're going to find that sine, cosine, and tangent can have transformations. In other words, they can be stretched, they can be translated. And all of those equations can be written in the form of y equals a times sine of k times theta minus c plus d value. And what we're going to spend most of the rest of the time doing is finding out what a, k, c, and d do. So let's do that. So I want to look at a first. What's the effect of a? Well, here's sine of x. That's the black graph. And then you'll see we have the blue graph of 3 sine of x and a graph of negative 4 sine of x. So you'll notice that in this case, they start and end in the same spot. So the period is the same. That hasn't changed anything with the a value. We notice that it appears that they're at a high point, or a low point for that matter, at the 3 pi over 2 and pi over 2. So that's the same as the original. And you'll notice that the only thing that's really changed is that the blue graph goes higher and the green graph goes lower. So what's happening is this number out in front acts just like the number in our previous problems. It's like a y multiplier, okay? But we call this a value the amplitude. Okay, and it's kind of the y multiplier. All right, and what it does is it basically is how high the graph is from the most center part of the graph. They call this right here, the middle of the graph, the midline. So it's the distance from the midline. In other words, this blue graph is 3 up from the midline and 3 down from the midline. Now, A is always how far, which means it's a distance or an absolute value. Okay? In the case of -4, if we ask what the amplitude is, we're going to say A is equal to 4, but this negative basically is a y multiplier. So instead of just going up 4 from the original, we multiply that y value by a negative, and that puts us down at -4. So it actually, -A reflects the graph. And that's over the x-axis. So next we'll see what the k does, and remember our k is a number that's a multiplier in front of an inner term. And we notice here the black again is sine of x. Notice I've represented 2 periods because here's 2 pi, here's 4 pi, so you'll see the black graph happens twice. Now if I take and make the k value 2, you'll notice, well, what has that done? It starts in the same place, but it ends in a different place. One period's going to end a lot quicker. All right? The amplitude remains the same, so the A value has not changed at all. And it's not translated, it's not moved left and right. This is normally starting at 0 and it's finishing at 0. So what this has done is it's basically taken this black graph and squished it down. So we're talking about k being an x multiplier. All right. And in this case, it doesn't make it twice as long. It makes it actually half as big, because our period of this sine of x is 2 pi. The period of sine of 2x is pi. So something's going on here. So k is not the period. It turns out that the period for sine and cosine is equal to 2 pi over k. Tangent's something different. We'll talk about that in a minute. All right. For tangent, we know that the normal period is pi, so pi over k is going to be the period for tangent. So now if we look at this yellow graph, if k is 1/2, that means the period is 2 pi over 1/2 multiplied by the reciprocal, so that's 4 pi. And you'll notice that it's twice as long as the black graph, which was normally a 2 pi period. So k again is a x multiplier. It changes the period, but it is not the period. Again, just a slide to spell it all out. A is the amplitude, acts like a vertical stretch or a y multiplier. K changes the period, or the time for one cycle of the graph to happen, acts like a horizontal stretch or an x multiplier. The periods are 2 pi over k, or if you're using degrees, 360 over k, that's sine and cosine. For tangent, because tangent has a smaller period to start with, the period is pi over k, or 180 degrees over k if you're using degrees. So now we're going to put this all together. All we've dealt with at this point are basically k values and a values, so we're going to lay them all out here. We know the a value is 4. Period, I'm not sure what that is, but I know it's 2 pi over k And k in this case is the number in front of the x, which is 1. So our period is 2 pi. Our intervals, those are pi over 2 for sine and cosine. And our C and D values, those are 0 because we haven't introduced those yet. Those are addition and subtraction values. So if I want to graph this, here's what I basically do. I'll go over and I'll start at 0 because that's where sine starts. I'll go in intervals of pi over 2, so that's pi over 2, pi, 3 pi over 2, and 2 pi. And then I will graph sine, but I need to note that instead of being 1 for my amplitude, it's going to be 4. So I start at 0, multiply the value of 0 by 4, and I get 0. This would normally be at 1. I multiply 1 by 4, and I get 4. There's my new amplitude. Goes back to 0. 0 times 4 is 0. Goes to negative 1 normally, but now it will go to negative 4, and back to 2 pi. So my graph looks exactly like sine, but it's been stretched out by 4 times. We know that this distance here from the midline is 4. So for the graph of negative tangent of x, I identify my amplitude of 1, but because there's a negative, I get a reflection over x-axis. And if you remember, our original tangent graph looks something like this. And again, this was a graph of 2 periods, not 1. We're only going to graph 1. Period is pi over k, and we know our k value is 1. So our period is pi. Intervals, we're going to keep those at pi over 2 for right now. And we'll note that in this case, what's happened is we've got C and D is still equal to 0 because there's no pluses and minuses. I'll start by going 0, pi over 2, pi. I only want 1 period, so I'm going to stop there. I know typically in tangent, have an asymptote at pi over 2 and at 0. And pi, I have values of 0 for the tangent. Normally, as you can see in this graph over here, tangent increases, but I'm reflecting all the y values because I'm multiplying each of them by negative 1. So instead of this rising, it's actually going to fall. Likewise, this falls. And that is 1 period of negative tangent. So now we're going to graph sine of 3x. This is where things are going to change a little bit. A is 1. The period in this case is 2 pi over k, or in this case, 2 pi over 3. Now, here's the issue. If this graph is going to do a sine motion no longer in 0 to 2 pi, it's going to go from 0 to 2 pi over 3. All these intervals of 1s and 0s are going to have to change as well. So basically what we do is we take our pi over 2, which is our normal interval, and we cut those by the k value, or a third. So our interval is pi over 6. So notice, if I have pi over 6 intervals, with C and D being 0, I start at 0, and instead of going to 2 pi, or pi over 2 to start with, I'm going to go to pi over 6. And I increase by pi over 6 every time. So this is 2 pi over 6, 3 pi over 6, and 4 pi over 6, which is 2 pi over 3. So, graphing sine, at 0, my y value is 0. At normally pi over 2, which is now pi over 6, I have a value of 1. I'm back to 0, down to -1, and back to 0. So here's my graph. Looks just like a sine graph, but instead of going from 0 to 2 pi, it's going from 0 to 2 pi over 3. So once again, it's an x multiplier. We're multiplying all the x values by a third. It's pushing the graph in or squeezing it and compressing it. This is tangent of a half x. Notice we have a k value of a half. So this again is an x multiplier. Okay? We're taking and basically dividing everything by a half or multiplying by 2. I know my a value is 1. Period, since it's tangent, is pi over k. K is a half. So we've got basically 2 pi for my period. All right. I also notice my interval is going to change. Normally that's pi over 2, but that's also divided by a half. So my intervals are now pi. C is 0, D is 0. Again, I'll start at 0. I will take and put an asymptote and another 0. Normally, we know that this is all going to happen from 0 to pi, but now what's happening is these are all going to be basically divided by pi over 2. So instead of this term here being pi over 2, it's now pi. Instead of this value being pi, it's going to be 2 pi. And then the tangent graph will look exactly the same, always increasing. If I want to graph y equals cosine of x, basically what we're doing is we're looking for the a value, which is 1. That doesn't change. The period is 2 pi over k, which is 2 pi over pi in this case, which is 2. My interval is normally pi over 2, but I'm taking and dividing that by pi, or multiplying by 1 over pi. So my interval is a half. C and D are both 0. Here's a cosine graph, so I usually start at 0 and go by pi over 2's, but I'm now going to go by half, so this is a half, 1, 3 halves, and 2. And then this is a cosine graph, so instead of starting at 0, 0, I know that the cosine value at 0 is 1, and then I go down to 0, -1, 0, and 1. So nothing, again, is changing in the shape of the graph. It's just either higher, lower, or more compressed. This, again, looks exactly like our normal cosine graph, except instead of going from 0 to 2 pi, it goes from 0 to 2. So now we're going to put both an a value and a k value into this problem. We have an amplitude of 2, so we'll multiply all the y values by 2. The period is 2 pi over a third, because that's my k value, which is like going 2 pi times 3, or 6 pi. My intervals, which were normally pi over 2, are now going to be multiplied by 3. So my intervals are 3 pi over 2. C and D are both 0. Again, it's a cosine graph, so I'll start at 0. I'll move in intervals of 3 pi over 2, so here's 3 pi over 2. Add 3 pi over 2 to that. That's 6 pi over 2. 9 pi over 2. And 12 pi over 2, which happens to be 6 pi. It's a cosine graph. It's going to look basically like our other graph. So I start at 0, and instead of 1, I'm going to be moving 2 high. So I come up here. Then it looks like a normal cosine function. Goes down to 0. We go down to -2, up to 0, and then back up to 2. And I just draw the graph from here. Like so. Next, we're going to be asked to write a cosine function. It says we've got an amplitude, so that's an a of 7, and a period, which is 2 pi over k. Of pi over 4. So let's just grind that out. We have 7 cosine of, this is basically going to be k theta or kx. It doesn't really matter. But k, we have to find that. We know that 2 pi over k is equal to pi over 4. I need to solve that. I can do it a lot of different ways. I'll take and do a cross product just for fun. So I multiply diagonally, and then I want to get k, so k in this case is equal to 8, and then y equals 7 cosine of 8 theta, or you could say 8x, it really doesn't matter. Same type of problem, except now we're dealing with periods in degrees. Okay, we have an amplitude of 2, so that's not a big deal. Period, it's a sine function, 360 over k. A we know is equal to 2, so we have y equals 2 sine. Now I need to find the k value, so the period is 540 equals 360 over k. Therefore, k equals 360 over 540. That is, let's see, 180 goes into that 2 times and 3 times here. So 2/3 theta. And then we've got to actually go backwards. Here's a graph, and we want to find the equation of this graph. And in order to do that, we're going to need to find the period and the a value to be able to write our equation. So in this case, the period, this looks like a cosine graph because it starts at 0 and has a high value. This should repeat if nothing has changed in 2 pi, and notice that's exactly what it does. Our period equals 2 pi. So that basically says k equals 1. And since our period is 2 pi, k must equal 1. Now the amplitude is how far this graph is from the midline, or that split between the high and the low. The midline in this case is 0, okay, and we want to know how high it goes up from 0. That's 5. So I can write my equation of y equals 5 cosine k, which is 1 theta. And then I'm done. Lastly, tangent. So now I look and I automatically know I've got a problem because I don't see any pi's down here, and these aren't degrees. Okay, these are going to be in radians. Radian x-axis. So I look, how long does this graph take to repeat? Well, I usually start, since I know this is a tangent, I look for the 0, 0, and then when it repeats itself. So the period in this case is equal to 4. And I know for tangent, the period is pi over k. So therefore, I can say that k is equal to pi over 4. Now, for tangent, basically what I want to do is I want to look at a specific point halfway between these two, because we found out earlier that if I split the interval of pi over 2, or normally pi over 2, in half, then we get a value at 1. And that's exactly what I have, so I know my a value here is equal to 1. Therefore, I can say that y equals tangent of pi over 4 theta. And that'll do it.